Hello. So this is section 1.6. What this section is three um, three ways we can apply. Let me rephrase that. Three real-world problems to which we can apply the row reduction techniques we've learned in sections 1.1 through 1.5. And so what I'm going to do is I'm just going to break each application up into sort of a mini lecture. The corresponding worksheet has three problems on it, or sort of three sections, or 3 pages, maybe even more accurately, corresponding to this section. And each one contains a different application. And so what I'm going to do is just go over each application in a different video. So first things first, we're going to go over an application to economics. So I'll go ahead and read the problem, and then I will talk about sort of the questions I have accompanying and sort of some ideas for how we can approach this and solve it. Suppose an economy has 3 sectors: chemicals, fuels, and machinery. Chemicals sells 30% of its output to fuels, 50% of its output to machinery, and keeps the rest. Fuels sells 80% to chemicals, 10% to machinery, and keeps the rest. Machinery sells 40% to chemicals, 40% to fuels, and keeps the rest. So, if you can think about what's going on here, you can think like, each of these sort of sectors of an economy, right? So, whatever economy this is supposed to be modeling, right? This is sort of modeling some smaller, sort of production going on. You can think of each of these sectors as having some sort of aggregate output, which you might measure in units or dollars or something. And so you're sort of saying, okay, like chemicals is going to always sell 40% of what it makes to X, sell 30% of what it makes to fuels, 50% of what it makes to machinery. And of course, that means it keeps 20%. And so, thinking about this is like, okay, 20% dollars, units, whatever sort of, I guess, we're going to use to measure what output is representing. We can model what's going on with what your book calls an exchange table. And so this is what this looks like. And the way this is read is if you go down the columns, you can look at what each sector is outputting. So this column here would, again, read chemical is keeping 20% of what it produces, giving 30% to fuels, and 50% to machinery. What this also tells you, if you read horizontally, is basically what each sector is receiving, right? So chemicals, obviously keeping 20% of its own output, it's receiving 80% of fuels output, and receiving 40% of machinery's output. So you can learn a lot just by looking at this table. And so what our goal is as economists in this problem, or mathematicians, is we want to be able to say, okay, chemicals should produce so many units, fuels should produce so many units, and machinery should produce so many units, so that we can reach what is called equilibrium. And so for this economy to reach equilibrium, I hope I spelled that right, each sector outputs as many units as it receives. That is, if we're measuring output in, say, dollars or total dollars, the chemical is outputting, say, $100, it should be receiving also $100. So, how do we know if an economy has reached equilibrium? Well, this is where math and linear algebra can come in, because we can model, say, we can model each output, right, by these variables p sub c, p sub f, and p sub m, right? So suppose these 3 variables represent the outputs of each sector. Well, we know an economy has reached equilibrium when its input is equal to its output, right? So if this is the output, well, then each output should equal oops, sorry, that should be a C, each input. And again, because we have this nice exchange table set up, we can just read horizontally in order to determine the input of each piece of M, and then 0.5 piece of C plus 0.1 piece of F plus 0.2 piece of M. So notice I've just assigned these sort of arbitrary variables, P sub C, P sub F, and P sub M to represent the outputs. But because we have sort of the percentage of output each sector is going to receive, we can also say, well, okay, here's P sub C's output, here's P sub C's input. These two things should be equal. And so the answer to question 2, if the economy is going to reach equilibrium, these are the equations we know must be satisfied. All right, so this looks an awful lot like a system of equations with 3 variables, 3 equations. So there's a likely chance it could be solved. But it's not really in a form that we know how to work with, right? So if we're going to apply linear algebra, we want, all of our variables on one side and all of our non-variables on another side. Right now, I've got these variables on the left-hand side of the equation. But thanks to, I guess, normal algebra, I can turn this into a homogeneous system of equations by just subtracting each of these outputs over to the other side of the equation. And so notice if I do that, I get the following system of equations that, again, if this system of equations is satisfied, then we know the system is at equilibrium. All right. And so notice now I've got a homogeneous system of equations, 3 variables, 3 equations. I can set up an augmented matrix and row reduce to solve. So we'll finish this up by doing a little bit of row reduction. So I'm going to start, I'll erase the top here, and then I'll start to work my way down. So I want to solve this system of equations for the variables P sub C, P sub F, and P sub M. Notice question 4 asks something interesting, right? So it says we want to solve for the equilibrium prices when the output of machinery is 100 units. So that should sort of lead me to believe that, oops, sorry, my phone is going off. That should sort of lead me to believe that we're going to get a free variable when we row reduce, right? The fact that I'm being given sort of this, okay, when this is equal to 100 units means if I row reduce this, I'll probably get some free variable. So keep that in mind. But notice here's the augmented matrix that we want to row reduce. And so as I'm doing this, notice we've got decimals for every entry, obviously, except in the last column. I don't like decimals, right? What is one valid row operation that I can just immediately do to get rid of these decimals and not actually change the values of my solution? And this is sort of just my own personal preference that for some reason decimals just annoy me. But notice I can multiply row 1, row 2, and row 3 all times 10. and just turn this into a matrix without decimals, and I've actually not changed anything about the eventual solution. And I'm only doing this because I hate decimals so much. Right. So now we can do some row reducing. All right, so first thing I'm going to do here is I'm going to divide row 1 by 2. Or sorry, I'm actually going to divide row 1, not by 2, by 8. So my reason for doing this, I know it adds a fraction, but when I notice like this 8 is going to become my pivot position, right? And so I'm going to use this 8 to clear out the 3 and the 5. And so what I ultimately want, it'll be easier for me, I guess, to make this 8 a -1 and live with this being a 1/2 than it will be to work with fractions sort of other ways. It's just sort of personal preference, doesn't really matter too much. But so next, now I'm going to use this -1 to clear out the 3, hence the 3 row 1 plus row 2. Then I'm going to use this -1 to clear out the 5, hence the 5 row 1 plus row 3. And something very convenient happens when I do that. I get the following new row 2 and row 3 entries. So I'm just going to do this. Now, I identify my next pivot, which is this -6. So I'm going to do -1/6 times row 2. I think I'm also going to do row 1 times -1, since I eventually want to turn this into a +1. And so that new row 2 becomes 0, 1, -11/12. And I'll make that a little more clear just to differentiate it from being over 2. All right, and so last thing we just now want to do row 2 plus row 1 and replace row 1. All right, and so remember what these variables correspond to. So I get the following system of equations. I get that the output of chemical minus 17/12 times the output of machinery is equal to 0, and that the output of fuel minus 11/12 times the output of machinery is equal to 0. And so remember now, we know that the output of machinery, or we've assumed that the output of machinery is equal to 100 units. And so this is just now a matter of multiplying these values by 100. And so PC would be 1700/12 units, and PF would be 1100/12 total units. And so if we want to achieve equilibrium, when machinery outputs 100 units, we should have chemicals outputting 1,700 over 12 units, and fuel outputting 1,100 over 12 units. All right, so that's first application. Next, we will look at an application to chemistry.